India topper. I crushed this paper to become the AS level chemistry India topper. But I hate chemistry. I know you hate chemistry too. So let two haters of chemistry work together to figure out how to tackle this irritating paper. Now, don't get me wrong. I am the AS level India topper for physics, world topper for mathematics, and best across three India rank 1. At IGCSEs, I was the world topper for mathematics, world topper for ICT, and an all India rank 3 holder. So, yes, I do have a pretty good understanding of how CAI works. However, I last opened my chemistry textbook 3 months ago in February when I attempted my A level exams. So, I'm as vulnerable to making a mistake as any one of you would be. With that in mind, let's solve the May June 2024 paper, the paper that made me the chemistry AS level India topper. Let's begin. The first question is about the periodic table. Complete table 1.1 using relevant information from the periodic table. We've been given two ions, Mg2 plus and Al3 plus. Their nucleon numbers have been given. We have been asked to identify their proton numbers and electron numbers. Now, we can identify from the periodic table that will be given to us at the end of the question paper that the proton number for magnesium is 12 and that of aluminium is 13. Now, I just remember it, but you can refer to it at the end in the table over here. So, magnesium is 12 and aluminium is 13. Okay, and now the number of electrons, because this is a 2 plus ion, so there will be two more protons than electrons, so there will be 10 electrons over here. And similarly, the number of electrons here will be 13 minus 3, because it is a 3 plus ion. There will be three more protons than electrons, so there are 10 electrons here as well. State and explain the difference in the ionic radius of aluminium 3 plus compared to magnesium 2 plus. So we know that across a period, the ionic radius decreases. We already know this from the periodic table. So the ionic radius, or Al3 plus, has smaller has a smaller ionic radius than Mg2 plus. Now we know that there are two major factors that affect the ionic radius. The first is the nuclear charge. So aluminium has a greater or a higher nuclear charge than Mg2 plus, because there are 13 protons compared to 12 protons. That is why Al has a 3 plus charge compared to Mg, which has a 2 plus charge. Okay, it is important to mention nuclear because the attraction is coming from the nucleus. Okay, second important factor is shielding. So number of electrons are the same, right? So if the number of electrons are the same, the shielding effect or the repulsion from electrons is also going to be the same. So, and shielding effect or shielding is the same. So electrons in Al3 plus experience greater nuclear attraction than in Mg2 plus, right? So if there's an electron here, let's say this is a nucleus, then an electron over here will experience greater pull, right? Because there's a greater charge, it will pull it more fiercely and to more closer than compared to a Mg2 plus ion with a smaller nuclear charge, right? Very simple. Next question. Draw a label diagram to show the structure and bonding in sodium. Now, sodium is a metal, so it will obviously have a metallic bonding. Now, we know the trick over here, right? A metal is made up of positive ions. It is made up of positive ions. So I can just show a lattice, right? Another thing that metals have is a lattice of positive ions, because sodium is a solid at room temperature and it will have delocalized electrons. Delocalized electrons. Okay, now another thing that I would really want you to take care of is to draw the same number of negative ions as the positive ions, because we have been asked to show the bonding in sodium, not a sodium ion, not Na plus or Na2 plus or whatever. It is Na, an atom, right? So that is why we will show the same number of negative signs as positive signs. Now, also, you want to show at least two rows with four positive signs each to show that it is kind of a lattice, right? And then we will label them. So I will say lattice of positive ions. Positive sodium ions. And I can draw a line here and say C of delocalized electrons. This will fetch me my 1 mark. Next question. Figure 1.1 shows the variation in melting point of some period 3 elements in their standard states at room temperature and pressure. Okay, so we're talking about melting points here. Explain why silicon has such a high melting point. Now, this is talking about atomic structure. So we know that silicon has a giant covalent structure, right? So I can say silicon has a giant covalent structure. So large amount of energy is required to break that structure, right? Large amount of energy is required to overcome strong intermolecular forces, right? Or strong bonds, whatever. But you need to mention that the bonds or the bonding is strong, and that is why the structure is giant covalent, and that is why the melting point is high. So we need to talk about bonding and structure for silicon. Complete figure 1.1 to show the variation in the melting points of the elements potassium, sulfur, and chlorine. Okay, now guys, this is a trick question, okay? Because if you have noticed, the graph of melting point against element has a very small nuance. The nuance is that the melting point of sulfur is higher than the melting point of sodium. Okay, so we have to pay attention to this little detail. So obviously, because the non-metals will have lower melting points than the elements, than the metals, the melting point will drop over here. So for potassium, I can have a melting point say over here. Okay, I'm drawing it with a pen here, so just please be lenient on me with that. And for sulfur, it will just be marginally higher than sodium. So I will have a line here, and then chlorine will be the lowest, so my line will come down. So you need to really sort of understand or memorize this graph for melting points against element, because there's just one little tricky nuance. Okay, another detail is that the melting point of chlorine should be lower than the melting point of phosphorus. So okay, I said potassium earlier, I think, I'm sorry, it's phosphorus, and chlorine is a gas, phosphorus is not a gas. So bearing that in mind, you will have to estimate the melting points. Okay, next question. Two period 3 elements react with an excess of oxygen at room pressure. Complete table 1.2. So that we have been given two elements, sodium, sulfur, state of oxide at room temperature pressure, and approximate pH of solution when oxide is added to water. Now, you just need to think this logically. When we have Na plus O, it gives us Na2O, which is sodium oxide. This will always be a solid, right? Obviously, until its melting point. But at room temperature and pressure, sulfur will form sulfur dioxide, SO2, correct? Or SO3. That is a gas. Now, when I add that to water, Na2O will give me NaOH and hydroxide. The hydroxide will be basic, and this will be a strong base. So that I can be approximated to a pH of, let's say, 12. And sulfur, SO2 or SO3, will give me a strong acid like H2SO4 or H2SO3. So I can say that has a pH of about 1 or 2, right? Because it is a strong acid. Okay, so these are the approximate pHs that we can estimate. Next, the solutions made in column 3 of table 1.2 are mixed together. So an acid and a base, if they are mixed together, there will be an acid base reaction or a neutralization reaction. Write an equation to describe the reaction between phosphorus oxide P4O10 and an excess of water. So P4O10 plus H2O. Now, I always recommend people to just remember the products and the reactants. Okay, balancing we can figure out on the day of the exam, but you need to remember what it will give you. So it will give us H3PO4, which is phosphoric acid. Now there are 4 phosphoruses on the left hand side, so I need 4 over here, 4 p's on the right as well. Now how many oxygens or hydrogens are there? We can compare that. So I like to compare hydrogen because that's simpler. So this, over here there is 3 times 4, which will give me 12 hydrogen atoms on the right hand side, and here there is 2 hydrogen atoms in 1 water molecule. So I need a total of 6 water molecules, and if you just cross check oxygen as well, this equation is balanced. Aluminium hydroxide is amphoteric. Explain what is meant by amphoteric. So amphoteric means it reacts with both acids and bases to form salts. Right? So this is your simple answer. It will give acid-base reactions with both acids and bases. Write an equation to describe the reaction when aluminium hydroxide reacts with NaOH. Now we know that this forms a special salt with the formula NaAlOH4. So how do we write that here? We have AlOH3 plus NaOH, which gives us NaAlOH. Next question. Separate samples of Na2CO3 and NaHCO3 react with HCl to produce the same products as shown in table 2.1. So we have sodium carbonate and sodium bicarbonate, and their reactions are given over here in the table. Okay. Now their enthalpy change is given as delta H1 and delta H2. Complete the reaction pathway for reaction 2. We have to show the enthalpy change and the activation energy. First thing that we want to look at is whether the reaction is endothermic or exothermic. So if you look at delta H2, it is positive, so the reaction will be endothermic. So I have to draw my bell here, like this parabola here, and then my straight line when the reaction ends. Okay, so I can draw a dotted line over here, and I can show my activation energy here with an arrow as EA, and my delta H2 over here as the enthalpy change. I also have to write down the products over here on the right hand side of the curve. Now, since I'm writing with my graphics tablet, I can't really fit it on this little blank here, but I think with a pencil, you should be pretty fine. Okay, this is our 2 marks here. The value for delta H1 is determined by using the following method. 50 centimeters cube of 2 mole per decimeter cube of HCl is added to a polystyrene cup. So always just mentally start visualizing the experiment. Okay, so there is a polystyrene cup over here. In that, they have added some HCl. Okay, now initial temperature of the acid is recorded. There's a thermometer, that means over here. Okay, 0.4 moles of Na2CO3 is added to the mixture. So I have added some Na2CO3 over here. Obviously it will settle down, but just for the diagram over here, and all the solid Na2CO3 disappears and a colorless solution is produced. The maximum temperature recorded is 26.2. Describe one other observation that shows the reaction is complete. Now we have 4 to 5 major physical observations that we can make. So first is obviously a color change or a precipitate forming. The second thing that we can obviously notice is the solid disappearing or a solid forming, that is a precipitate. Okay, the third major observation, if we are using a flame, is a flame test. The fourth major observation, a physical observation that we can make, is hydration or condensation at the mouth of the test tube. And the fifth observation that we can make is the presence of gases. So either we see bubbles, we see effervescence, okay, and if it is a colored gas, we can see some fumes coming out of the test tube. Okay, but the gas that is being produced here is carbon dioxide. It is a colorless gas, so we can't see the carbon dioxide being produced, but we can definitely see the effervescence. So describe one observation that shows the reaction is complete. That means the effervescence that was happening has now ended. Effervescence has stopped. So that is my answer. Okay, next question. Calculate the value of delta H1 in kilojoules per mole. Assume the specific heat capacity of the reaction mixture is the same as for water and no heat is lost to the surroundings. So for water, the specific heat capacity C is equal to 4.18 joules per grams per Kelvin. Okay, so this is something that you have to remember. But let's see the experiment. So I can first calculate the temperature change. Okay, so I can calculate the temperature change was 26.2 minus 19.6, which will be equal to 6.6 degrees Celsius. Okay, now I can calculate my energy change, which is equal to mc delta t. Right now, m stands for the mass of water, or the mass of the solution that is being taken. So we have taken 50 centimeter cube of HCl. So because it is a very dilute solution, we can take the mass of the solution to be equivalent to the mass of water. So that will give us 50 grams, because water has a density of 1 gram per centimeter cube, times 4.18 times 6.6. So my energy change is going to equal 1379.4 joules. Okay, joules, not kilojoules, but joules. Okay, now next thing that we need to take care is the amount of the entire solution, or the amount of the reactants that we have taken in moles. Okay, so we need to identify which of the reagents here is the limiting reagent. So we will calculate the amount of HCl. So n HCl, or the moles of HCl, is going to be 50 centimeter cube into 2.00 mole per dm cube. Right? N equals C into V. We will use this formula to find our answer. So N over here is going to be 50 upon 1000, because we have to convert it in decimeter cube into 2, which is going to equal 0.1 mole. Right? And the moles for Na2CO3 over here are 0.04. Right? Now, the next thing that we need to take care of is the ratio. So 1 mole of Na2CO3 reacts with 2 moles of HCl. Right? So the ratio is 1 is to 2. So that means 0.04 moles, okay, 0.04 moles of Na2CO3 reacts with 0.08 mole of HCl. So what does that tell us? We only need 0.08 moles of HCl, but we have 0.1 mole of HCl. Now, guys, don't be confused, okay? It is very simple. We need 0.08 moles, okay? But we have 0.1 moles. So we have more than what we need. So that means HCl is in excess. Now, whatever is in excess, we don't take that quantity. We take the limiting reagent, which is the Na2CO3. So we will take the Na2CO3, which is the limiting reagent, okay, and this will, so our delta H1 is going to be 1379.4 upon 0.04, and because the reaction is exothermic, we will add a negative sign to it. Okay, so 1379.4 upon 0.04 gives me 34,485 joules per mole. Right, this gives me 34,485 negative joules per, sorry, yeah, 5, this is 5 joules per mole. So that will give me negative 34.485 kilojoules per mole. Now this has become a little, shabbier, but I hope you get what I mean. Okay, so my answer is negative 34.485. You can round that off to negative 34.5 or leave it as that. Both will score you your full marks. Okay, thermal decomposition occurs when any. Okay, for just the purpose of clarity, I'm going to erase everything over here. And let's just hope that, sorry, 485. Yeah. Let's solve this Hess law question right here. So over here, we have three sodium compounds. We have Na8CO3, Na2CO3, and NaCl, right? So we have three compounds. Now, both Na8CO3 and Na2CO3 will give me NaCl. So let's write NaCl over here, Na8CO3 over here, and Na2CO3. This is how you have to form a Hess cycle. Okay, this is a very rough cycle, but I think this should serve the purpose. Now, the second thing that we need to consider for your Hess cycles are stoichiometry. They are the underrated heroes of Hess cycle. So for every 1 mole of Na2CO3 over here, I have 2 moles of NaHCO3 over here. Okay. Then for every 1 mole of Na2CO3, I have 2 moles of NaCl over here. Okay. So 1 mole of Na2CO3 will give me 2 moles of NaCl. And for 1 mole of NaHCO3, I have only 1 mole of NaCl. So if I add 2 over here, I will also add 2 over here. Okay, I am ignoring the acids and the waters and the carbon dioxides for now. So this means that I have this Hess cycle because I have been given the reaction for NaHCO3 to NaCl. I have been given the reaction for Na2CO3 to NaCl, right? And I have also been given this reaction 3. So this over here, this is your delta H1. Oh, sorry, 2, delta H2. This here is delta H1. If you just look at the reactions, we have our enthalpy changes as delta H1 and delta H2. And this is delta HR, which we have to figure out. So the change from, we are calculating the enthalpy change from 2NaHCO3 to 2NaCl. Now I can take this direct route of delta H2, or I can take this entire route that goes from NaHCO3 to Na2CO3 and then back to NaCl, right? So I can take this longer via route, but my start point and end point are always going to be the same. Always pay attention to the direction of your arrows. Okay, make sure your arrows are facing in the same way. So now in this case, I can form one equation that delta H2, because the enthalpy change for a particular start point and a particular end point is going to be the same. So delta H2 is equal to delta HR plus delta H1. Now, over here, there is one big mistake that we are making. The mistake is that delta H2 only accounts for 1 mole of NaHCO3 and 1 mole of NaCl. So if we have doubled the moles, we need to double the enthalpy over here. Okay, and now we can just simply substitute delta HR is equal to 2 delta H2 minus delta H1. So if I substitute, that gives me delta HR is equal to 27.2 into 2 minus 34.485, right? Minus of minus gives us plus, guys. Always remember the algebra. So 27.2 times 2 plus 34.485, which will give me 88.885 or 88.9 kilojoules per mole. Yeah, my PC just crashed. Okay, let's solve this question now. Z is a salt that contains a period 4 element from group 2. When Z is heated, brown gas forms. Identify the formula of Z and use it to write an equation for the reaction. So we know that Z has one part or one ion, which is a period 4 element from group 2. So let's just scroll to our periodic table. Group 2 is here and period 4. So 1, 2, 3, and 4. The fourth period, this gives us calcium. So that means calcium is one of the ions, or rather the metal ion. Now we need to find out the anion. Okay, so when Z is heated, that means there's a thermal decomposition reaction. Brown gas forms. Now we know that calcium ions can either have calcium hydroxides, or they can have calcium carbonates, or they can have calcium nitrates, which will decompose thermally in the scope of your AS level syllabus. So the brown gas forming indicates that there is a nitrogen dioxide as a product. Okay, that means that the only possible anion over here is a nitrate. Okay, so we have identified Z, that is calcium nitrate. Identify the formula of Z. So whenever we want to identify the formula of Z, what do? We identify the cation and the anion, and then we just use them to match the ratios in which we will need to combine them to make a neutral ionic compound. So I will need two NO3s to make, 2 minus to cancel out the 2 plus and the calcium, to give me an overall neutral charge. So my formula will be CaNO3 2. Okay, and because it is a thermal decomposition, this will be my only reactant, and this will give me CaO firstly. Secondly, it will give me NO2, and thirdly, it will give me O2. Now I can just balance this quickly. So 2, 2, 4, and this is obviously 1. So this is my entire reaction. Okay, you can ignore this part. Next question. Describe what is meant by dynamic equilibrium. So here we know there are two conditions. Firstly, rate of forward reaction equals rate of backward reaction or reverse reaction. And secondly, we know that concentration of reactants and products is constant. Okay, one mistake a lot of students make is they write the concentration is same. No, it is not necessarily the same, right? Otherwise all the Kc values would be 1. No, it is not the same, it is constant, it is fixed, right? There may be more reactant than the product, but there are ratios there, they are fixed. Reaction 4 describes the reversible reaction between yellow Fe3 plus and colorless SCN minus to produce red FeSCN2 plus, which is Fe3 plus SCN minus is reversibly giving you FeSCN2 plus. An equilibrium mixture contains Fe3 plus, SCN minus, and FeSCN2 plus. A few colorless crystals of soluble KCN are added. The mixture is then left until it reaches equilibrium again. The temperature of both equilibrium mixtures is the same. Okay, so if there's the temperature is the same, that means that temperature as a factor affecting equilibrium is taken out. Okay, we don't know the pHs of these solutions, so we also take that out of the equation. So the only factor that is changing over here is the concentration, because if I add KCN into the mixture, that will increase the concentration of SCN minus ions. Okay, so deduce the changes that occur in the change, okay, in the change in appearance. So if the solution, or if SCN minus concentration rises, that means that the equilibrium will shift to the right, to balance the change in concentration of SCN minus. So the change in appearance would mean that the solution is more redder and less yellower, right? Change in relative concentration of Fe3 plus. So relative concentration decreases, right? Because now if the equilibrium is shifting to the right, that means more of the product is forming and the reactant concentration is decreasing. So relative concentration, pardon my handwriting, decreases. The change in the value of the equilibrium constant Kc. Now Kc is always given by product upon reactants, right? So there are two reactants, so I will have SCN and Fe in different brackets here, but Kc only and only changes if there is a change in temperature. Because the temperatures of both equilibrium mixtures are the same, there will be no change in the value of Kc, right? Because relative concentration of Fe is reducing, but the relative concentration of SCN is increasing, right? So they both increase and decrease in such a way that this constant Kc remains the same. Okay, the expression for the equilibrium constant Kc for reaction 4 is shown. 5 into 10 raised to minus 5 moles of Fe3 plus, okay, and same moles of SCN minus are added together and allowed to reach equilibrium. Okay, so this is my initial moles. Some of these moles will be converted into FeSCN2, that is my product. Okay, but initial moles have been given to me. Total volume of mixture is 25 centimeter cube. Calculate the concentration of FeSCN2 plus. At equilibrium, the concentration of FeSCN2 plus is 4.23 into 10 raised to minus 4 mole per dm cube. Calculate the value of Kc. Okay, so I can first calculate the initial concentration of Fe3 plus. This will be equal to 5 into 10 raised to minus 5 moles. It mole per dm cube is the unit, remember. So mole upon dm cube. So I need to convert my centimeter cubes to dm cube. So that will give me 25 into 10 raised to minus 3. This, if I put it into my calculator, that gives me 2.0 into 10 raised to minus 3 mole per dm cube. Okay. Now, because the values of the moles of SCN2 minus SCN minus is also the same, so I can say initial concentration of Fe3 plus, SCN minus is also equal to 2.0 into 10 raised to minus 3 mole per dm cube. Now, always remember, guys, the initial concentration of this product was 0. So, how much of a product is formed, that much of the reactant is taken away from the initial moles, right? So, if we look at the stoichiometric equation, the ratio is 1 is to 1 is to 1. So, if 1 mole of FeSCN2 plus forms, 1 mole of SCN minus reduces, and 1 mole of Fe3 plus reduces, right? So 4.23 into 10 raised to minus 4 mole per decimeter cube of FeSCN2 plus, so the product is formed, right? So that many moles per dm cube of my reactants is taken away or is reduced and is used to make that product. So my final concentration, or Fe3 plus, that is equal to the concentration of SCN minus. Now I can use this notation because this notation is given to me in the question. Okay, is going to equal 2 into 10 raised to minus 3 minus 4.23 into 10 raised to minus 4. Okay, so 2.0 into 10 raised to minus 3 minus 4.23 into 10 raised to minus 4, which gives me 1.577 into 10 raised to minus 3 mole per dm cube. Now I have all my three concentrations, so I can substitute into the equation, which will give me 4.23 into 10 raised to minus 4 upon 1.577 into 10 raised to minus 3. And because both of these values are equal, I can simply square my denominator. So I will get my answer as 170.08. So it comes up to 170 to three significant figures. Now the units, there is 1 mole per dm cube here and 2 mole per dm cube in the denominator. So the unit over here will be mole raised to the power of minus 1 and dm to the power of cube, right? So answer is 170 mole raised to the power of minus 1 dm raised to the power of 3. This is your answer. Determine the full electronic configuration of Fe3 plus. So if I just look at my periodic table, Fe is at a proton number of 26. Okay, so that will give me 1s2, 2s2, 2p6, 3s2, 3p6. Now Fe has a proton number of 26, but that is a 3 plus ion, right? So that means there will be 3 less electrons than your Fe atom. Now generally we start with 4s2 and then we fill up the remaining 3d orbitals. However, in an ion we know that the orbitals are lost from the 4s orbital first and then from the 3d orbital. So that means this comes up to be 18, right? So 2 plus 2 is 4, 4 plus 6 is 10, 14, and so 10, 12, and 18. And then the remaining 5 electrons will be from the 3d orbital. SCN minus is colorless. Complete the dot and cross diagram in figure 3.1 to show the arrangement of outer electrons in an SCN minus ion. Okay, so now if we just look at this over here, carbon has a valency of 4. That means it can form up to 4 covalent bonds. Sulfur has 2 electrons that can form covalent bonds, and nitrogen has 3. So 2 plus 3 will give us 5. We know that carbon can form only 4 covalent bonds. That means this extra electron or this extra covalent bond that is being formed is going to be the reason for my negative charge. Okay, so now let me just make my 3 bonds with nitrogen first. Carbon nitrogen bonds. Okay, there's a little wait. Yeah, let's just start again. I hope I can fit it, please. Yeah. And nitrogen also has 1 lone pair of electrons, so I need to draw them as well. Now, so carbon has only 1 electron left to donate. So I can make this electron over here. That means only 1 pair of electrons will be donated by carbon to form a covalent bond between carbon and sulfur. Now, sulfur could have formed a dative covalent bond with carbon. However, carbon's orbitals are already full because there's 2 electrons here and 6 electrons here. So there cannot be any more electrons in these 2 intersections. That means all the remaining electrons must go into sulfur's shell. Now, sulfur has these 6 electrons that it originally had, and there will be a 7th electron that sulfur accepts, and this 7th electron is the reason for my negative charge. This is that extra electron that SCN minus accepts, which causes the negative charge. Okay, now for your answer, always give a key. So a key which starts with, say, a filled circle is an electron from N. A cross is a carbon electron, and a hollow circle is a sulfur electron. Now I have written EL with an ellipse. Please write the full word. Okay, next. Okay, my PC just hung, but let's resume. Fourth question. CH3 CH2 5 times CH CH3 exists as a pair of stereoisomers. Draw the 3-dimensional structures of the 2 stereoisomers of this compound. R can be used to represent the entire CH3 CH2 times 5 group. Okay, now we have entered organic chemistry territory, and the first question is about stereoisomers. At the AS levels, we know there are only 2 types of stereoisomers: geometric and optical. Geometric stereoisomers at AS levels requires you to have a carbon-carbon double bond. But in this compound over here, there is no carbon-carbon double bond. That means there will be an optical isomerism displayed over here. Okay, now we need to find chiral carbon, which means that has 4 different groups attached over here. So obviously it cannot be the carbons on the left and right, the extreme carbons, because they have 3 hydrogens, so they are not chiral, right? The carbons in the middle over here, they are repeated units and they have 2 hydrogen attached to them, so they cannot be chiral either. That leaves us with this carbon over here, which has 1 hydrogen, 1 bromine, 1 methyl group, and 1 R group, right? So we can draw a 3-dimensional structure like with the carbon in the center. Okay, we write, let's say, CH3 over here. Okay, over here we can have, let's say, R. Okay, now going backwards here is, let's say, bromine, and into this plane, let's say we have hydrogen. This is one structure, and then the other structure will be exactly the mirror image of the structure we drew over here. So this will be CH3. Okay, R will be this side, H will be this side, and you will have Br over here. A sample of CH3 CH2 5 CH reacts with NaOH to make CH3 CH2 5 CHOH CH3 in an SN1 mechanism. So this is basically nucleophilic substitution. Complete figure 4.1 to show the mechanism of the reaction of this compound and NaOH. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Okay, perfect. Very simple, guys. Now we know that it is an SN1 mechanism because it is a secondary halogenoalkane. So it can either do SN1 or SN2, but SN1 has been specified to us. If it was a tertiary halogenoalkane or a primary halogenoalkane, then we know it would react with SN1 and SN2 react mechanisms respectively. Okay, now over here we can notice that this carbon atom over here will have a delta positive charge. Always start with your dipoles, and the bromine atom, which is more electronegative, will have the slight partial negative charge or the delta negative charge. So that means that the carbon bromine bond is going to break, and bromine will take both of the electrons. So this will be a heterolytic fission of the carbon bromine bond. Okay, now we know that because it is SN1, in the first step OH minus will not be formed. OH minus will not be found. Sorry. Yes. Okay. Now we have OH minus over here. In our second step, we start with OH minus, and you always want to prefer putting the lone pair of electrons on the oxygen atom, not the hydrogen atom, because that is the site of the lone pairs. Okay. Now we have our carbon atom, our hydrogen, our CH3, and I always prefer to put this group on the right because that just gives me a lot of ease to work with. But you can also put it on the left, doesn't really make a difference. So we get CH3, CH2 5 times. Okay, now we also need to notice that this carbon atom is positively charged. So I can give a positive charge. This is a negative charge. Now, the negative charge is not being attracted to the positive charge. The lone pairs are being attracted, okay? Because this is going to be a covalent bond, not an ionic bond. So the charges are not attracting. The charge is definitely helping in the bonding, but the lone pair is attracted to the carbocation. Okay, so this, we will have an arrow over here, a curly arrow over here, and we also need to show that this bromine over here will now become a bromide ion, right, with a lone pair of electrons. So this is the entire second step that you need to show for your entire 3 marks. Okay, next question. Separate samples of CH3, CH25, CHBr, CH3, CH3, CH25, CHOH, CH3, and CH3, CH25, CH2 are tested with different reagents. Okay, so if we just notice what mess this has been created, so this over here we have to just focus on the functional groups. So this is a secondary alcohol. Okay, this is an alcohol. This here is a bromide, a halogenoalkane, right? A halogenoalkane. And this over here is a simple, it is a simple alkane. Oh no, it is an alkene. If you see this CH over here and this CH2 over here, they both have a double bond, right? They're both missing a hydrogen each. It should be CH3 at the end, right? They're missing a hydrogen. So this is an alkene. Okay, now we just need to write about the observations. So we know that bromine decolorizes alkenes, but there is no reaction with other two functional groups. So over here we can say that solution turns orange to colorless, right? Bromine liquid is orange, and then it will decolorize to become colorless. And here, if no reaction occurs, give a cross. So we can give a cross. Next, BCl5 with an alcohol. So we know that there will be a substitution reaction that will take place. This OH minus, this OH group will be replaced with a chlorine group, right? And if you have read the textbook clearly, if you have made your own notes, we know that HCl as a gas will be given with this reaction at the end, right? You will get HCl. So HCl will give you misty or steamy fumes, right? So I can write steamy or misty fumes, right? And with this alkene, I will not get any reaction. Finally, silver nitrate with my bromide here. So I know that with a halogenoalkane, silver nitrate will give me a precipitate. Okay, now the color of the precipitate depends on the type of the halogen. Is it chlorine, is it bromine, or is it iodine, right? So bromine will give me a cream precipitate, right? So just white, cream, and yellow. So bromine will give me a cream precipitate. And this will not silver nitrate will not react with an alcohol. So this is your answer. Okay, now don't be afraid to put the crosses, just trust your reactions. Okay, so for the entire organic, I really recommend you to make a list or mind map, whatever works for you. For me, mind maps were really confusing, but make a list of all the organic reactions, their reagents and their conditions. So once you have understood all the reactions and the reagents and conditions, you know the pathways any organic compound can take to become another compound, right? And so you will trust yourself to put in these crosses and not try to overthink. Next question. This CH3, CH2, CHBr, CH3 is heated with D to produce three different molecules, E, F, and G. Now, if you notice, I can see some type of stereoisomerism. Okay, but we can see an alkene being formed. Okay, so D should generally be NaOH in ethanol, right? Because we know that this is an elimination reaction. So the type of reaction is elimination, because this Br and one hydrogen from here is being eliminated to form HBr, right? Plus HBr. Identify D and the conditions used. So NaOH in ethanol gives you my 1 mark. Next, both pi and sigma bonds are present in a molecule of E. Complete 4.2 to show the number of carbon atoms with each type of hybridization in one molecule of E. So sp hybridized, okay, will mean that there's a triple bond. sp2 hybridized will mean there's a double bond, and sp3 hybridized will mean there's a single bond, okay, with carbon carbon bonds. So we need to identify the number of carbon atoms. Okay, we don't need to write the number of sigma and pi bonds. If we were talking about sigma and pi bonds, we will also consider the CH bonds. But since there's only the number of carbon atoms, we just focus at the carbon molecules over here. So in E, both of these carbon atoms, okay, which have a double bond, will be sp2 hybridized. And since there is no triple bond, there's no carbon carbon triple bond, there will be zero sp hybridized molecules. And all the remaining carbon atoms, so 1, 2, 3, 4, 5, and the last one 6, all of these will be sp3 hybridized. Describe the essential feature of an unbranched hydrocarbon that causes its molecule to show stereoisomerism. Explain how this feature leads to stereoisomerism. Now, we just need to talk about unbranched hydrocarbons. So there can never be optical isomerism, because if there is an unbranched hydrocarbon, okay, there will not be 4 different groups attached over here, right? So that means that it is going to be geometrical stereoisomerism. Now, geometrical stereoisomerism always and always needs a presence of carbon carbon double bond. This bond includes one pi bond, right? So in the carbon carbon double bond, one bond is a sigma bond, one bond is a pi bond, and we know that pi bond is a lateral overlap of p electrons. So when this lateral overlap takes place, the repulsion is so high that you can't really rotate around the plane of the collision, or the plane of the overlap of the p bonds. Basically, in a pi bond, there is a restricted rotation about the carbon carbon double bond. So I can say which restricts rotation around or about carbon carbon oops sorry carbon carbon bond. Okay, now because of that, explain how this feature leads to stereoisomerism. Okay, now because of that, if there are different groups attached, okay, I'll just erase this joker of a C over here in the middle. So if there are different groups attached to each carbon atom, there are different arrangements of of the compound in free space and time, or free space, right? So that means that in space I can have two different three-dimensional or arrangements of a particular atom with the same structural formula. Okay, now that is basically the definition of stereoisomerism. That is that, compound with the same structural formula but with different arrangement of atoms in free space. I am just basically quoting that definition over here to justify my claim previously. That is why understanding the definitions is also pretty important for your chemistry paper. Compound W has molecular formula C4H10O. It contains only one functional group. Table 5.1 shows the two peaks with the greatest Me values in the mass spectrum of W. Calculate the relative abundance X of the peak at Me equals 75 using a table from information from table 5.1. Now, if there are two peaks, right, with very close Me values, then this closeness could be affected by few elements. So one element is carbon, right? So there could be a carbon 12 isotope or a carbon 13 isotope. Another element that affects peaks is chlorine, right? There's chlorine 35, chlorine 37. Again, another thing is bromine. So if there's a difference of one, then it is carbon. If there's a difference of two, then it is either chlorine, bromine, iodine, whatever, right? And all of these have ratios. So chlorine, say, has a ratio of 3:1. So 35 has a ratio of 3, and 37 has a ratio of 1 in natural environments. So similarly, carbon 12 is to carbon 13. The ratio in the environment of both of these isotopes is 100 is to 1.1. So there's 1.1% chance that a carbon 13 atom exists as compared to 100% chance of a carbon 12 atom being existing. So there is a 100 is to 1.1 ratio of carbon 12 is to carbon 13 atoms naturally existing in the environment. So the relative abundance, or X, is going to be 1.1 into 50 upon 100, which will give me 0.55. The mass spectrum of W also shows peaks at Me equals 29 and Me equals 59. So that's the molecular formula of these fragments. So if I just noticed, I have to find the sum of the formulae, the sum of atoms in this compound W's formula from C4H10O, which will give me a relative molecular mass of 29. So for 29, I can have C2H5, right? That sounds like a pretty decent combination. So 2 into 12 will give me 24 plus 5. So that gives me C2H5, and always add a positive sign because we have taken a mass spectrometry. We have ionized these fragments. And 59, I can start with an oxygen that will give me 16. Okay, and then if I remove 59 minus 16, that gives me 43. So let's say I remove two further carbons. So I remove 24. That gives me 19. Let's say I remove another carbon. Okay, so I have removed 12 more. Now I have 7. So I can have, let's say, 7 hydrogens. So C3H7O plus. Now just remember that it should be a logical, sensible group. You just can't really have 4 carbons and 1 hydrogen, because there cannot be a group like that with just 4 carbons and 1 hydrogen, right? So you just need to take care that such a group can possibly exist. Okay, next, a sample of W is heated under reflux under acidified K2Cr2O7 until there is no further reaction. Only one organic product, X, is present in the mixture at the end of the reaction. Figure 5.1 shows the infrared spectrum of W. Okay, so we just need to complete it, table 5.3 using the information given here, and in table 5.2. So A over here is at a wave number of about, say, 3200, 50 to 3500. That is in the half towards 3500 wave numbers. Okay, so over here this is arranged as in ascending order. So if I see, I can have only two particular functional groups, that is an amide or a hydroxy, right? But my compound W does not have a nitrogen molecule, so it cannot be an amide. So it is only possible that it will be an hydroxy, right? So I can have an OH, and the bond is OH, functional group will be hydroxy. Now X is after W has been heated with an excess of K2Cr2O7 until there is no further reaction. So my guess is that if it is a, it depends actually whether it is a primary alcohol or secondary alcohol, that will determine if it is giving me a carboxylic acid or a ketone, right? But here if I just see the wave number, it is somewhere between 1500 to 2000. Okay, so if I have a C double bond O, okay, I have here a carbonyl carboxyl group over here. Okay, and yes, I have a carbonyl or a carboxyl group somewhere in this range. C double bond O. Okay, now how do I figure out whether it is a carbonyl or a carboxyl? Now, the trick to doing that is to look at other peaks. So I have another peak somewhere around 3000. Okay, now if you look at the table over here, I have a peak for carboxyl at 2500 to 3000 as well. I do not have another peak for carbonyls. So if it was a carbonyl, I would only have got one peak. If it was a ketone, I would only have gotten one peak and not this 3000 peak here. So that is why this is going to be a carboxyl or a carboxylic acid. So this means the structure over here of the acid over here will give me C, 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 C. I can first draw the C's. Okay, I have an OH, O double bond H. Sorry, and then I can just fill up the H's in the remaining spaces. This is the displayed formula. You can write the structural formula as well. Both will give you marks. Okay, next. Y is a structural isomer of W. Both W and Y produce colorless bubbles when sodium is added to them. Y does not react when heated with acidified K2Cr2O7. Y does not react when warmed with alkaline I2. That means Y does not have a CH3CO group. Okay, and secondly, Y does not react when heated with K2Cr2O7. So if it produces colorless bubbles, that means it is an alcohol. Yes, it is an alcohol. Okay, and if it does not react with acidified K2Cr2O7, it means it is a tertiary alcohol, right? So over here, if we just take this thing here, this will give us C4H9ONA plus H2. So I can have 2, 2, 2, and this will be my reaction. The functional group present over here should be hydroxy. Okay, and draw the structure of Y. So a tertiary alcohol here, CH3, CH2. I'm sorry. COH. Yeah, CH3CH3. I think this should be the answer. And tertiary alcohols do not react in the alkaline I2 test either. So that is your entire chemistry May June 2024 paper. If you enjoyed, if you understood something, and if it helped you, be less nervous about tomorrow, please make sure to like this video and subscribe to my channel. If you have any questions, comment them down below and I will make sure to solve them as soon as possible. Thank you so much. Have a good day and I will see you guys in the next video. All the best. I am sure you will rock it. And yes, for the record, I still hate chemistry. Bye bye.